Hi there, AP Pre-Calc. It's Jean Adams from Flamingo Math. We're in Day 2, Chapter 4, Lesson 14. We're finishing up this unit looking at matrices and modeling in context. Remember in our last lesson we saw the market share for Bluetooth earphones leveled off after a period of time using the recommended advertising campaign? Well, that matrix is called a stationary matrix, and the system is said to be in a steady state or a state of equilibrium. Now, does every Markov chain have a unique stationary matrix? And will each successive state matrix always approach this stationary matrix? Well, the answer is yes for a regular Markov chain. So you're asking, what is a regular Markov chain? A transition matrix P is regular if for some power of P has only positive entries. A Markov chain is a regular Markov chain if its transition matrix is regular. And we're going to see that those properties are there's going to be a unique stationary matrix S that can be found by solving this equation. S times P of X is S. And given any initial state matrix S sub naught, the state matrices S sub k approach the stationary matrix S, and the matrices P to the k power approach a limiting matrix we'll call P bar, where each row of P bar is equal to the stationary matrix S. In example 5, they want us to look at which of the following matrices are regular. In example A, you can see all of the values are positive. So yes, this is a regular matrix. But in example B, matrix P has a 0 in that lower right-hand element. So to begin with, it's not regular. But if we find a different power, notice that the P value squared, if we calculated the first few powers, we're going to get all of the elements are positive. So now we can say it is a regular matrix. And then finally in part C, if we square, we have zeros on the diagonal. So if we square matrix P, we're still going to get zeros on the diagonal, but it's going to be the opposite way. If we find another power of P, say P cubed, that's P squared times P, it's just going to go back to being 0, 1, 1, 0. And if we find another power, say P to the 4th, it's going to be P cubed times P. It's still oscillating 1, 0, 0, 1. So no matter how many powers of P we apply, it will not give us a regular Markov chain. Okay, suppose, for example 6, suppose the transition matrix for a regular Markov chain is given as T. Show that if you take higher powers of T, T to the n, as n becomes large, it approaches a state of equilibrium. Find the stationary matrix by raising the transition matrix T to a large power, T to the n. I started out with T to the 20th power on my calculator. And you can do that just, I know on my Inspire, my keystroke sequence is math 7 and then 1, because I'm going to create the matrix and enter those values 8/10, 2/10, 6/10, and 4/10. And then after I've made that matrix, I hit the up arrow to the 20th power and end up with 3/4, 1/4, 3/4, and 1/4. So we've shown that we do have a stationary matrix as it approaches some very large power. Continuing on in that example, suppose the transition matrix is P, and we want to find the stationary matrix S by solving S times P of X equals S. So I hear what they're saying is I want some AB to be multiplied by P, 8, 2/10, 6/10, and 4/10, and I want the answer to be AB. So how do we do that? So first, let's write a system of equations that represents this matrix multiplication. We have 8/10 of A plus 6/10 of B has to equal A, and 2/10 of A plus 4/10 of B has to equal B, and A plus B has to give us 1. So we have this system of equations. We can substitute, so first we got that. We can substitute that A is 1 minus B. So let's go approach that. So 8/10 of A, that's 1 minus B, plus 6/10 of B has to equal A, that's 1 minus B. Solving for B, we've got 8/10 minus 8/10 of B, and 6/10 of B is 1 minus B. So combining like terms, add this B. We've got 8/10 of B is 1 minus 8/10, so that's 2/10. That gives us B is a quarter. And back over here, if B is a quarter, A has to be 3/4. So that's not so bad. Does your result from part B match the result from part A? Well, what do you know? Yes, it does. So we have, yes, our AB matrix is 3/4 and 1/4 in both of those methods. So we got that steady state, raising it to the 20th power, I believe, is what we got. Yes, raising the transformation to the 20th power, or using a system of equations. Let's try one more application problem here. Brightline is a new Florida high-speed train service that goes from Miami to Orlando. In the first month of operation, it's expected that 15% of the commuters are using the system in the Miami vicinity, but 85% are still traveling by car. The matrix below was determined from records of other large rail systems. We want to know, what is the initial state matrix? Well, the initial state matrix is 15% and 85%. So we're going to call that S sub naught, 15% and 85%. And what percentage of commuters will be using the new high-speed train after 1 month and then after 2 months? So again, you can use your calculator to figure this out. S sub 1 is the 0.15 and 0.85, and we're multiplying by this particular matrix. 6/10, 4/10, 3/10, 7/10. And we find in the first month, we've moved up to 34.5% and 65.5%. In the second month, we're finding S sub 1 times the transformation of X bar, which turns out to be 0.4035 and 0.5965. So in the first month, we have 34.5%, and then after 2 months, we have 40 and 3/35%. So this is the first month. Month 1 is 34.5%, and month 2 is 40 and 3/35%. Part C, what percentage of commuters are using each type of transportation after the high-speed train has been in service for an extended period of time. Again, not to overtax my calculator, but if we try the transformation of x at the 20th power, so 20 months later, and you can try several, you can try 21, 24, and see if this becomes a steady state on your calculator. We find that about 42.9, almost 43%, will now be using the new train, but there's still about 57.1% will still be driving their own vehicles. Okay. And then example 8, well, first we have to talk about regular Markov chains again. I think we covered this, but let's just review. A Markov chain is said to be regular if some power of it has only positive entries. If we let T be that transition matrix for a regular chain, and we take higher powers of T to T sub n for T to the nth power as n gets large, it approaches a state of equilibrium. Excuse me. If S sub naught is any distribution vector and E is an equilibrium vector, then S sub naught times the transformation is going to be that equilibrium vector. So we already saw that, steady state. Each row of the equilibrium matrix is a unique equilibrium vector, E, so that E times T gives us E. This is just stating things that we already know in different language. And then predicting past states, we want to work backwards here. The product of the inverse of a matrix that models transition between states and a corresponding state vector can predict past events, past states. Recall from the previous lessons when solving matrix equations in the form of AX equals B that we could find a solution for A by using the inverse matrix where A is B times X inverse. So we can consider that you know the transition matrix for a widget that your company produces. You also know the state vector for 1 month of an advertising campaign. That state vector at 1 month is given as 30% and 70%. We want to know, can you find the initial market share for your company using inverse matrix operations? So that's what we just read in the notes above. We can do that. We want to find T inverse of X bar. But first of all, can we do it? Let's see. We need the determinant for this matrix A. So 0.6 times 0.8 minus 0.2 times 0.4. So the determinant of A, we're going to multiply 6/10 times 8/10. 0.48 and 2/10 times 4/10 is 8/100. So the determinant is 0.4. To answer the question, can you find the initial market share for your company using inverse matrix operations? Yes, we can, because the determinant is not 0. So to find the inverse matrix, we want to take 4/10 and the inverse, we switch the 8 and the 6, so 0.8 goes here, 0.6 goes here, and then the 2/10 becomes negative, and the 4/10 becomes negative. So what does that give us? 8/10 divided by 4/10 is going to be 2. Negative 2/10 divided by 4/10 is going to give us a half, but it's going to be negative a half. 4/10 divided by 4/10 would give us -1 here, and then the lower right, 6/10 divided by 4/10 would give us 1.5 there. So here is our inverse matrix using those earlier properties of matrices. In the next example, can you solve the matrix equation? So the distribution vector S sub naught is our B times the inverse. So the work for that, S sub naught has to be our B, which is 3/10 and 7/10 up above that steady state 1. And then our inverse we just found 2, -1, -1/2, and then 1.5. And performing those operations, we're going to get 0.6 minus 0.35, and then -0.3 plus 1.05, if I did that right. Okay, so we're going to get our steady state. Our initial is 0.25 and 0.75. So this is our initial. We found the S sub naught. In part C, can you explain what the initial market share of your product based on your calculations? So what happened initially? Your company has 25%, has a 25% market share. What are we creating here? For our widget. What is the steady state in part D, or the long-term market share for the company? Explain how you know. I'm going to get 1/3, 1/3, and 2/3. I know because over a long-term campaign, the campaign will help your company gain a 33.33% of the total market share. And how did we do that? Well, I took the calculator and entered the first month, which was 6/10, 4/10, 2/10, and 8/10. And again, I like 20 on my calculator so I don't overstress it. And got the values 0.3 repeating and 0.6 repeating in all 4 elements. So I knew I had that steady state there. Okay, we got one more day in this lesson and we're finished with chapter 4 in AP Pre-Calc. Join me tomorrow.